Sir, are you speaking?
Let you take it. I will definitely not remember. சொல்லுவீங்களா எங்கேயாவது ரிமைண்டர் வச்சுக்கோங்க. Okay, shall we get started? Those who are online, am I audible?
Yes, sir.
Is that you?
Yes, sir.
Okay. Listen. Okay. Sorry. Listen. So we'll start with the next chapter that is called as electromagnetic induction. Okay. So the next chapter is called as electromagnetic induction. And if you look at the name of this chapter, right? Electro refers to charges, right? Magnetic obviously refers to magnetism. So when you talk about induction, it means there is no physical contact. So if you look at the fourth chapter, right, what did it speak about? It spoke that moving charges generate magnetism. Means if magnetism needs to get generated, you need to put the charges in motion, right? The obvious question that will arise is there a possibility of doing the reverse? In the sense, can you use magnetism to generate electricity? Right? That is what this chapter speaks about. So that is why if you see, when I say electromagnetic induction means induction is generating something, inducing something, right? Without any physical contact. So what is getting induced? The charges which are in motion, that is electric current, is induced with the help of magnetism. Am I clear with this point? Right? So, having said this, the first and the foremost top, the first and the most important topic that we need to understand in this chapter is magnetic flux. So we need to understand what is magnetic flux. If you see, magnetic flux is almost similar to that of electric flux, except the fact that there we use the electric field lines, here we are going to use the magnetic field lines, right? So what does magnetic flux speak about? So magnetic flux is spoken about or through any surface which is placed in the presence of magnetic field. So what does it state? It is the total number of magnetic field lines crossing the surface normally. So if there is a surface through which you want the magnetic field lines to pass, if you're able to calculate the number of magnetic field lines which are passing through the surface perpendicular to it, then that number is what is called as magnetic flux. So like how electric flux is represented with the symbol phi, magnetic flux is also represented with phi, but the subscript B is used. So if you use E, it is for electric flux. If you use B, it is for magnetic flux, right? So listen to this carefully. This is the statement. Total number of magnetic field lines that are passing through a surface normal to it. That is a statement. But the question is, how are you going to calculate that number? You need a mathematical formula. Mathematical in the sense you need something to quantify it. You know what is the meaning of quantifying, right? Give a value to it, right? For that, we have another definition, that is, it is a product of component of the magnetic field normal to the surface and the surface area. So that is the mathematical definition, but let's try to understand why it has come in the first place. See, suppose I have the field lines in this manner. They are parallel to each other, and there is a surface like this. There is a surface kept like this. So this is the direction of field, right? What is the direction of aerial vector to the surface? This is the direction of aerial vector, right? Aerial vector is always perpendicular and it is in the outward direction. This we have learnt in Gauss law itself, right? It is in the outward direction. So if I take this as A, makes sense? This is the aerial vector and this is going to be B. If I take this to be theta, right? If I take this to be theta, then the magnetic field can be resolved into two components. What are they? One is, this is B cos theta and the other is going to be B sin theta. So the B cos theta component, right? The B cos theta component multiplied with A is what is going to give us the magnetic flux. So phi B is equal to B cos theta multiplied with A. Or you can also call it as BA cos theta. So this BA cos theta, if you observe, B is a vector, A is also a vector. So you can write this as B vector dot A vector. Make sense? Right. Now the question is it a scalar quantity or a vector quantity? Obviously, a scalar quantity because it's a dot product between two vectors. Right. Secondly, what is going to be the SI unit for it? If you look at the unit for it, it is going to be Tesla meter square. So this Tesla meter square is what is called as WEBER, which is Weber. So the unit of magnetic flux is Weber, right? So that Weber is derived as a product of Tesla and meter square. So that is why if you see in previous chapter and all, right, when we solve some problems, they would have given B is equal to some 2.5 Weber per meter square. We would have seen this. So Weber is there. If you bring the meter square to the right hand side, what will you get? You will get Tesla. So Weber per meter square stands as a unit for magnetic field, whereas Weber stands as the unit for magnetic flux. Is the point clear? Right? So this is the most important term that we need to understand before we start the chapter itself. Okay? Just make a note of it.
They wrote normal to the surface.
Normal to the surface means parallel to the aerial vector. Surface to normal, parallel to aerial vector. Shall I proceed? So the question is, why are we even speaking about flux? Right. So let's see, what is the main objective of this chapter? See, this is a simulation lab, okay? This is a simulation lab where we are going to understand about, 1 minute, I'll speak again, okay? So this is a simulation lab where we will be concentrating on the different parts that are there. See, first thing, you know about a bar magnet. So what happens to a bar magnet? It has magnetic field around, which can be sensed by a device called as compass. So you're going to place it and you're going to draw the field lines around it. You're able to see the field lines. The red color ones are called as the North Pole and the white is called as the South Pole. So you know how to draw the field lines for a bar magnet. There is nothing for me to explain, right? Next is, there is something like this. Okay, I'm going to show you two things. Observe. You have something like this, which is a coil and a compass, right? These blue color dots are the electrons, right? So if you pass current through this, right? If you pass current through this, in the sense when the electrons are flowing upwards, okay, let's try to understand. So which side, when you're seeing it from this side, when the electrons are flowing upwards, what is going to be the direction of current? Current will flow downwards. So when you see from this side, right, current is going to be in the anti-clockwise direction. So when it is going to be anti-clockwise direction, what pole is it supposed to be behaving as? It should behave as a north pole. So when you place a compass there, which pole should be closer to it? So is it happening? Is it happening? So south pole of the compass is closer to this. Makes sense? Now, if I reverse the direction, of it, observe what is going to happen to the electrons. Look at the compass. So the electrons started moving in the anti-clockwise direction. So current is in the clockwise direction. So it is going to be south pole. So when it is south pole, the north pole of the compass will be closer to it. Makes sense? So this is all we learned in the 4th chapter, because this is an electromagnet, in the sense electricity is generating the magnetism. So when there is no electric current through it, right? When there is no electric current through it, what is going to happen? So there is no magnetic field around it, as simple as that. So that is why this is called as an electromagnet. But what does this chapter state? We need to do the reverse. So for which we have this thing. So if you observe, we have a coil here, right? We have a coil and we have a magnet, right? So for this coil, this is going to be the axis. I place the magnet along the axis. Observe what is going to happen when I move this magnet, right? Something happened. So what happened? So when I moved the magnet closer to this coil, you could see that there is some current that is getting generated due to is the bulb glow, right? So there was a glow in the bulb. So whether I moved the north pole closer or whether I moved the north pole away, you could see that there was something that happened to the bulb and it got shut down as soon as I stopped moving it. Whereas if I move it continuously, you're able to see that it is going brighter and again dim, brighter and dim. Is it happening? Right? So this is what happens in a device called as generator also. See, what I'm going to do is I'll create an automated system. You're able to understand? So when this is rotating, there is current that is getting generated where it is flickering. This is what is called as an alternating current, right? Which is the leading factor for the next chapter. But something important is happening here. What is it? When this magnet is rotating, or when the magnet is moved, there is an electric current that is getting generated. So for this, we need to give a reason. So that is what we will try to give it in this chapter. Am I clear with that? Right? I want you to concentrate. Listen. So if I move the magnet, there is current that is getting generated. Now the question is, what if I move the coil? So it's still working. What if I move both of them? It will still work. So it clearly tells me that if there is a relative motion, listen to this carefully, if there is a relative motion existing between whom? Between the magnet and this coil. This coil is called as pickup coil because it is the one which is picking up the magnetism. Right? That's what is written here. It's called as a pickup coil. Okay, this is picking up the magnetism due to which it is generating the current. Right? So when there is a relative motion existing between the magnet or magnetic source and the pickup coil, not necessarily always a permanent magnet should be there. There can also be a temporary magnet, but you need some magnetic source, right? So when there is a relative motion between the magnetic source and the pickup coil, then the pickup coil will start having some current flowing within it. This is the overall objective of this chapter. This is the first point we need to understand, right? And this is an experiment done by Faraday, right? Based on which there is a law that is proposed. Am I clear with that? Right? Now, the question is, why is this happening? So when you move this magnet, right, or when you move the coil, what exactly is changing due to which this phenomenon is observed? There is something that is being observed for sure. This happens also because generators are designed based on this concept only. But what exactly is happening? What theory are we going to give to it is what the question is. Thing is, instead of a coil, if I had an open conductor and I moved this magnet, right, you cannot observe the current flowing through it. So that clearly tells me one thing, that I cannot have an open conductor. I only need to have a coil. So if I have a closed surface, if a closed surface has a magnetic field flowing through it, then it is easy for me to define a parameter called as magnetic flux. So that is the reason why we discuss magnetic flux as the first topic of this chapter. So when I move this closer, right, what is happening? Where is the magnetic strength more? Is it near the poles or pole? So when I move the north pole closer to this, I could see that I introduce more amount of magnetic field inside this coil. Hence, I increase the flux. Right? In a similar way, when I brought the magnet away from it, I try to reduce the number of field lines through this coil. So I try to decrease the flux. So in both the cases, what I did is I actually changed the flux within this coil with respect to time. That is why I told relative motion is important. As soon as the motion stops, the flux is going to be the same. See, for example, in this case, the same number of field lines are entering. Whereas when I move, what I'm doing with time, I'm changing the amount of flux. So if there is a change in magnetic flux taking place with respect to time, then there is an EMF induced in this coil. And because of that EMF only, the charges are actually moving. Am I clear? So whatever I gave you as a statement is what is Faraday's law of electromagnetic induction. Am I clear with this? Right? So the same thing happens here also. In the generator also, observe it is still rotating. Right? So when the north pole is coming here, flux is increasing. When the south pole is coming here, flux is increasing. But look at the direction of electrons. When north pole is coming, the electrons are moving downwards. When the south pole is coming, electrons are moving upwards. Why that is happening, we'll see it later. Am I clear with that? Right? So having said that, we will first look into the topic of Faraday's law of electromagnetic induction. So write down the heading. Right? So as I told you, right, the first thing that we need to see is Faraday's experiment. So the experiment number 1 is you have a pickup coil. So along the pickup coil, what happened is there is a magnet that is moved closer to it. So when the magnet is moved closer, the north pole moves closer, what will happen? The magnetic flux is increasing. What about this? When the north pole is moved away, the magnetic flux is decreasing. Whereas when the north pole is kept constant, when the magnet is kept constant, when the velocity is 0, what is happening? there is a constant magnetic flux within it. So in these two cases, things that were observed is the galvanometer shows some deflection, means there is some current flowing through it. Whereas if the magnet is stationary, the galvanometer shows null deflection. So this is the magnetic source, and this is what is called as the pickup coil. Is that clear? This is experiment number 1. Experiment number 2 is, what can happen is the magnet is kept stationary, but the coil is moved. Magnet is kept stationary, but the coil is moved. Still, what is happening? The flux is going to change, because when the coil was stationary, there is certain number of magnetic field lines that are entering the surface. When it is moving away, it is going to decrease. When it is decreasing, there is again a deflection that is shown in the galvanometer, right? And the third experiment is something like this. So along the same core, right? Along the same core, what is happening is there is one coil which is connected to a battery. So this is an electromagnet. In the previous two cases, we used a permanent magnet. Here we are using an electromagnet. So what will happen is, as soon as the key is closed, before the key is closed, what is the current through the circuit? 0. But as soon as it is closed, the current is going to increase from 0 to a certain number. So during the process of increase in value, can I say that the amount of flux associated with this coil is going to change? See, initially when the current was 0, what is the flux associated with this coil? Current is 0, magnetic field through this is 0, flux is 0. Because what is flux? VA cos theta. So unless there is no magnetic field, where am I going to define the magnetic flux? So when the current is going from 0 to a steady state value, during the growth process, magnetic field will increase. When magnetic field increases, there is a change in flux that is associated with this coil that will take place, due to which the galvanometer will again show some deflection. So in all the 3 experiments, we could understand one thing. What is it? If there is a change in magnetic flux taking place with respect to time, you can induce EMF in it, right? And that's what is given under the laws of electromagnetic induction, which says, Faraday's law of electromagnetic induction, which states that EMF is induced across the coil when there is a change in magnetic flux taking place with respect to time. Is that point clear? So E is directly proportional to delta phi B by delta T, where this delta phi B by delta T is called as the average value. So it is called as the average value. Now, if you remove the proportionality symbol, the constant that we are going to introduce is -1. So it is going to be minus delta phi B divided by delta T. And this negative sign is an indication of another law called as Lenz's law. So there are 2 laws we'll be learning in this chapter. One is Faraday's law of electromagnetic induction, and the second is Lenz's law. So these 2 are the building blocks of this chapter, right? And both of them work together. They are not individually treated. They both work together. So that's what is given in this mathematical expression. If suppose there is a situation where you don't have enough time for you to measure how much the flux is changing, then you will be calculating the instantaneous value. So what can happen is EMF can also be minus d phi b divided by dt, which is going to give me the instantaneous value. So if you want the instantaneous EMF, you use minus d phi by dt. If you want average value, you're going to use minus delta phi by delta t. Okay. See, suppose the coil has n number of turns, you will just put n here. If the coil has n turns, you will just put n here and n here. Okay. Is that clear? Yes. So make a note of this. Done? Okay. Because you connected the key, no, you opened the key and switched it off. After the current becomes constant, you cannot see. I told you, no. As you can see the deflection in the galvanometer only till the time there is a change in magnetic fields. So I told you clearly, before the key was closed, the current is 0. But to reach from 0 to that steady state value, it will take some amount of time. So during that time, you can see that there will be a deflection in the galvanometer. That's what is given. It's like one of the moments captured. Okay, again, if it stops, if the current is going to become a steady state value, then the galvanometer will come back to null. Is that clear? So are you done writing this? Right? So I told you about this minus sign, right? About this Lenz's law. I'll just give you the statement for it also. In this slide is our right. So the next topic is going to be about Lenz's law, for which we need to go to this table again. Yes, one. Right. So now we will discuss about the Lenz's law, the significance of that minus sign in Faraday's law. Right. I want you all to observe one thing very clearly. I'm going to ask you questions. So listen. When I move this north pole closer, observe how the electrons are moving. And when I move the north pole away, see how the electrons are moving. Okay. It was very faster. Listen. Still couldn't capture. Okay. Downward or upwards? Downward. So I'll move this north pole away. Upward. Makes sense? Okay. Now I'll bring this coil this side. I'll bring the coil this side. Now I'm going to move the south pole closer, see how the electrons are moving. It was fast. Okay. I'll do it again. Downward. So if I move the south pole away, was it upwards? We'll do it again and see. Upwards, right? So just to validate this, maybe we can use the generator and see. Observe. When the north pole is moving closer, so when the north pole is moving closer, the electrons are moving downward. When the south pole is moving closer, the electrons are moving upward for this side, right? So I don't know if I can move this. Speed. I'm not able to move this. Okay. So is that point clear? So when the south pole is moving closer from this side, the electrons are moving downward. And when it is moving away, it is moving upward. Right. Now tell me one thing. When I move the south pole close, the electrons move downward. Now, what is the direction of current? So upward in the sense, when you see from this side, is it going to be clockwise or anti-clockwise? Clockwise means what pole is getting generated? South. Meaning, when you're trying to move the south pole closer to it, what pole is getting generated? South pole. Whereas when you try to move the south pole away from it, what is happening? The electrons are moving upwards. So current will be anti-clockwise. So north pole. Meaning, when you took the south pole closer, south pole got generated. When you took the south pole away, north pole got generated. So now we'll change the directions and see. So here what happened? When you move the north pole closer, the electrons are moving downward, right? So when you see from this side, right? When you see from this side, if the electrons are moving downward, current is going to be in the anti-clockwise direction. So when it is anti-clockwise, north pole. So when north pole is moved closer, this side. When the north pole is moved closer, north pole is generated. When the north pole is moved away, so current is moving. So electrons are moving downward or upward. Observe. So observe. Upward. No, electrons are moving upward. So current is going to be clockwise. So this will be south pole. Did you observe in both the scenarios? When you try, whether you try to take the south pole or north pole closer, the same pole got generated. That's the thing happened. No, when I moved the south pole closer this side, south pole got generated. When I moved the south pole away, north pole got generated. When the magnet was this side. So this side, what is happening? When I moved the north pole closer, north pole got generated. When I moved the north pole away, south pole got generated. So now understand, minus is always written only when there is an opposition that is taking place. So we wrote E is equal to minus delta phi by delta t. No, that minus sign speaks about the opposition that is offered here. In the sense, whether you move the north pole close or south pole close, all that you did is you tried to increase the flux. So when you try to increase the flux, what pole was getting generated? Same pole was getting generated. So north pole moved closer, north pole generated. South pole moved closer, south pole generated. So why did it get generated is because if you're trying to increase the flux, the pole that we get induced here will be in such a way that it will try to decrease the flux. So you try to increase the flux by doing what? By moving the pole closer. But what was the coil trying to do? The coil was saying, I will decrease the flux by producing the same pole because like poles repel. In the second case, what happened? When you try to move the poles away, exactly the opposite happened. When you try to move the north pole away, it's saying I'll generate south pole here. When you move the south pole away, it told I'll generate the north pole here. Meaning, when you try to decrease the flux, it is saying I'll generate the opposite polarity so that I will try to attract it and increase the flux. So it will exactly do the opposite of what you're trying to do. So that is why we put a minus sign. Right? So this story clearly gives us a statement for Lenz's law. Right? I'm going to give you now. Just make a note of it. But before that, are you all clear with this concept? Did you understand? Right? So to put it simple, say when you move the pole closer, what pole will get generated? Same or opposite? Same. When you move the pole away, opposite. That's it. So here Lenz's law states induced current in the coil will be in such a way, induced current in the coil will be in such a way that it will always oppose the cause. That it always try to oppose the cause. In the sense, if I have a coil like this, let's say I'm having a magnet here, which has north pole and south pole. If you try to drop this magnet, right? So you're trying to bring the north pole closer, means you're trying to increase the flux. So what pole should get generated? There should be a north pole. So there should be an anti-clockwise current that is flowing in this. Sorry. So it is north pole. So when you see from the top, it is like north pole. Right? Whereas when you try to move the north pole away, what is going to happen? when you try to move the North Pole away from it, what will happen? There will be a South Pole that is generated. Are you able to understand this concept? So this is the meaning of opposing the cause. In the sense, why we are calling it as opposing the cause is because if you try to increase the flux, this will try to decrease the flux. If you try to decrease the flux, it will try to increase the flux. Is the point clear? See, these two are the building blocks of this chapter, right? If you are able to master Lenz's law, right? Why I'm saying master Lenz's law is because the problems are slightly tricky. Okay. So if you're able to master it, 85% of the chapter is over. Remaining things is only making you understand what are the values. So this is the toughest part. Okay. It's not yet over. We'll do some problems based on. Shall I proceed? Yeah. So now we'll try out some problems that are based on magnetic flux and the laws of electromagnetic induction. Okay. So first one is magnetic flux formula is BA cos theta, or it is also written as B vector dot A vector, and induced EMF is given as minus N into d phi by dt, where N is going to be the number of turns in the coil, right? D phi by dt means it is going to give you the instantaneous value. Suppose you want to calculate the average induced EMF, then it is written as E is equal to minus N into phi 2 minus phi 1 divided by delta t. Or you can just write it as delta phi by delta t also, right? And lastly, if there is a question based on induced current, then first find out the induced EMF divided with the resistance of the coil, because I is equal to V by R. So delta E divided by R. So I'll write it clearly. I is equal to, sorry, not delta E, modulus of E divided by R. Is that clear? So this is a summary of whatever we have seen till now. Shall I proceed? Shall I proceed? Listen. So the first problem is a rectangular loop of area 20 centimeter into 30 centimeter is placed in a magnetic field of 0.3 Tesla within its plane. Right? First, normal to the field. Second, inclined 30 degrees to the field. Third, parallel to the field. Find the flux linked in the coil in each case. So there is a rectangular loop which is placed in a magnetic field with its plane. First, normal to the field. Okay, since it is given as 0.3 Tesla, it is clearly understood that it is going to be a uniform field, right? So when it is uniform field like this, which is going to be 0.3 Tesla, first you place the plane of the coil perpendicular to the field. So this is the direction of field, this is the plane of the coil. So if the plane of the coil is perpendicular to field, listen to this carefully. Plane perpendicular to field implies B vector is parallel to A vector. Because one common mistake that we do is wherever we see normal, no, because what is the formula for flux? Flux is equal to BA cos theta, no. When we see the word normal, you put theta is equal to 90 and then solve it. You will get the wrong answer. So when plane is perpendicular to the coil, then aerial vector is parallel to the, correction. When plane is perpendicular to the magnetic field, aerial vector is parallel to magnetic field. Makes sense, right? So that's what happens here, right? So in the first case, phi 1 will be equal to BA cos theta, where theta is supposed to be 0 degrees. So it is going to be BA cos 0. How much is the value of B? 0.3. How much is the area? 600 into 10 power minus 4. So 600 into 10 power minus 4 or 6 into 10 power minus 2. So answer will be 1.8 into 10 power minus 2 Weber. Okay. Second question. In the second question, what they are saying is the plane is inclined at an angle 30 degrees. So plane is inclined at an angle 30 degrees to the magnetic field. So if this is the plane, for instance, so if the plane is inclined at an angle 30 degrees means the axis of the plane is making an angle of 30 degrees with the plane, with the field, sorry. Then what is the flux in the second case? I'll use the same formula BA cos theta. So how much will be the value of B? It is 0.3. How much is the value of A? 600 into 10 power minus 4. And what should be the value of theta that I need to take? Theta should not be taken as 30 because 30 is the angle made by the axis. But you need to take the angle made by the aerial vector. So if axis makes 30 degrees, aerial vector makes 60 degrees. Is the point clear? So cos 60 means how much is it going to be? Everything will be the same except the fact that this will get divided by half. So answer will be 0.9 into 10 power minus 2 Weber. Clear with that? So what about the flux in the third case? It is placed parallel to the field. So the coil is placed parallel to the field. In the sense, aerial vector is in this direction. Aerial vector is like this. Magnetic field is like this. So angle between them is 90. So I'll get cos 90, BA cos 90, which says the answer is 0. So there is no flux linked at all. Am I clear with that? Just give me a minute. Let me check the answer. 1.8 into 10 power minus 2, 0.9. Correct. All the three are correct. Understood? Right. See, this is just a problem that is based on magnetic flux. We didn't see a problem based on laws of electromagnetic induction. Clear? So there are a few more problems to be done. For this class, we'll stop with this. Okay. Next class, try to have your NCERT with you. Because I'll be showing you the diagrams here, but it will not be that clear. I can't zoom and show. That is a problem. So have the NCERT with you, only then I can explain it clearly. Is the point clear? and revise these concepts and come. So next class, we'll concentrate only on problems. On Monday, we'll concentrate on the laws of electromagnetic induction and Lenz's law. And Tuesday, you remind me about that thing, velocity selector and the torque. Okay. So any other questions? All clear? We'll close.
Thank you, sir. Thank you, sir.
Yeah, you can leave.
No, sir. I said thank
Okay.
you.